Okay. So I will present a little bit about my master thesis. It's about stovepipe radio interferometry and the novel approach to imaging the sun and observing solar flares. So in general, I want to start with the motivation why we are building radio interferometers. So the main goal is obviously to achieve a higher resolution, which depends on the wavelength and the dish diameter. And you can easily imagine if you want to have a similar resolution as in the optical astronomy range, then you will need a very large diameter for your dish. And at the same time, if you want or achieve these large diameters, then you have certain physical limitations with the movability and the pointing and stability and also spacing and costs, of course. So the solution for modern instruments is to build interferometric arrays of several smaller dishes. So how does this work? In general, if you start with a large dish and a common focal point, then you can separate these into smaller segments. So 1 to 8 here, and they also get a separate focal point, and then you don't have to keep them in this parabolic shape, but you can put them on the ground. And later on, if you use the data and correlate them, then you can basically create or synthesize a large dish again and also create an image of your original astronomical source that you were observing. So the objective of this project was to create a new setup, because at the University of Bonn in the master course, there's already a setup, but that is very weather dependent. So the idea was to create one that is not so weather dependent and also very easily to move and play around with. So it was created as a transit instrument with a digital complex correlator and of course affordable, cost-effective instruments. And then we used 3 elements. Before it was only 2 elements, and the main target in this case is the sun due to limited sensitivity. And since it's a new setup, there's also a need for new analysis software. So I'm also going to talk about this later on. And the goal or idea of it is to get the idea of the working principles of radio interferometry and then also get an insight into the data reduction steps, what is important later on. So how is this talk going to work? First, I will give a little bit of an overview on the theory, not too much into depth. And then we'll talk a little about the new setup and the setup testings that we performed, and then the analysis pipeline. And since we are already currently in the 25th solar maximum, there's also some flares occurring, so we could observe them, and I'll talk a little bit about them later. And then as a last step, we also extended this interferometry setup to smaller dishes instead of the stovepipe setup. And lastly, just a conclusion and outlook, what you can do with the instrument. So for the theory, since the main target of our observation is the sun, here is a spectrum on the right side for the sun in the optical regime, and then also going to the radio regime, where you can see a difference between the quiet sun and then the disturbed sun. And the disturbed sun obviously is the maximum of the solar cycles, where you have these solar flares occurring. So there's a big power difference when you observe the solar flares. Then a little bit about the layers of the sun, which are important in the radio regime. Mostly the outer layers of the sun, so the photosphere, the chromosphere, and the corona. And depending on in which wavelength regime you are observing, then you see the different layers of the sun. So that's essentially to know. So the setup that we are using is operating in the centimeter regime. So we are essentially looking at the chromosphere. Then a little bit about interferometry in general. So first, or in older times, they used adding interferometers. So they add the 2 signals of both dishes together. But the latest improvements are towards complex correlators because they're not so dependent on gain stability and they're more stable. So in general, they are mostly in east-west alignment, and the astronomical source that you're observing is in the far field. So you have a plane wave incident to your dishes, and as you can see in this setup, in this case, the source is towards the theta angle. So what you see is that the signal from the astronomical source reaches the right dish earlier than the left dish. So therefore we have a geometrical delay, which then basically is responsible for your fringe pattern at the output. So what is done with your digital correlator is that you'll get a real part and an imaginary part, so a cosine and a sine part. And going from those, you can then go on and calculate the visibility, amplitude, and phase. And how is that connected to your astronomical source? So your astronomical source is at the sky, and you normally refer to it as the intensity. And at the ground, you have your twin element interferometer setup with your baseline d lambda. And we introduce a new baseline coordinate frame with these u, v, and w coordinates, which depend on the hour angle and the declination of your source. And due to Earth rotation, your baseline coordinates change over the day, so you'll get ellipses in your UV plane. We will see that later in the analysis pipeline. And at the same time, you are limited to your baseline setup, therefore you're only sampling specific visibility values. But from these visibility values, you can then go on and create an image, so reach the intensity of your astronomical source via a Fourier transform. So this is essentially the theoretical part of interferometry. So now we'll go on to the setup. So before we worked on our final setup, we had a proof of concept measurement with our stovepipe antenna, and then on the right side you can see the correlation, real and imaginary part, over a time frame, and of course the sun was used for the observation. So since we saw that the proof of concept measurements were successful, we then could go on and have a fixed setup. And also the stovepipe in this case is working as a circular waveguide. So essentially you'll have a stovepipe and at the end a reflecting end cap and then a probe inserted, which you can basically kind of see in this image beneath the LNA and the aluminum box in this case. What's so good about the stovepipe or circular waveguide in this case is that you have a clear cutoff frequency, and also in this case, by having it at a specific position and a specific length of the probe, you can make it resonant to your specific observation wavelength in this case. So the setup, as I already said, is a 3-element, so an east, middle, and west antenna. And the antennas already are connected to their low noise amplifiers, which are then also connected to a bias T, so there's no extra cabling going up. And the middle antenna is splitted the signal from the middle antenna, and then we have two software-defined radios, the ADA and Plutos, which most of you already know from previous talks, and they are in dual channel mode, so one SDR gets the east and the middle antenna, and the other SDR gets also the middle and the west antenna. These two SDRs are externally clocked, and then the SDRs send the IQ data to a computer where the further processing is performed. So in this case, why do we need to split the signal from the middle antenna is due to the two different Plutos, because they have a time offset. So when we want to correlate the data between the east and the west antenna, then there is an offset which we need to correct for. So you calculate an autocorrelation of the middle antenna from the two Plutos, and then you'll get a time offset. And if you correct for this time offset, then you can also go ahead and correlate the east and west antenna. So you get a 3-element interferometer instead of 2 elements. So of course, setup testing now. Calculating far field is an easy calculation, which you can go ahead and do. And we are obviously in the far field because the maximum baseline in our case was about 10 meters, and the sun is far away in that case. So then you can go ahead and also kind of get the power amplitude for all the 3 different antennas for different bandwidths, and then you'll see it's a linear relationship, which is also expected. And as I already said in the setup section, that we'll need to autocorrelate the middle antenna to reach the correlation between the east and west antenna. This also then resulted in a bandwidth limitation of 2 megahertz, because if we increase it, then we'll have sample loss at the other and Plutos, and the correlation between the east and west antenna is lost basically. Then you can also go ahead and check for the RFI saturation at your specific setup location, and then have an idea of which center frequency you want to choose for your observations. And in our case, it's 1419, so close to the 21 centimeter line for hydrogen measurements. And on the left side, you can see an example of RFI pollution at another frequency. And in this case, the power amplitude is plotted against the time frame, which is always in the UTC time frame in our case. Then you can see the different spikes which occur. So it's heavily RFI polluted, and therefore you want to choose another center frequency, which ultimately led to the one that we chose. So what we also saw right at the beginning, and which I also presented at one of the SARA Zoom meetings, is that we had an interference pattern in the power signals, so not in the correlation that we observed. So it's also more pronounced in the morning sessions. And the idea was that it is a ground reflection, so similar to multipath interference, or if you do sea interferometry, that's actually the mechanism they are using, that the reflection of at the sea towards your antenna. And well, it was not directly proven that it is a ground reflection, but it is very likely, because at the beginning, when we were doing the experiment, the grass was very short, so it kind of built a reflective surface. But later on, this interference pattern disappeared, which is most likely due to the grass. The grass was not mowed, so it kind of grew over the summertime, and it was not building one reflective surface anymore. And of course, what is very important, we talked about the geometrical time delay. What you have to keep in mind is that due to the cabling going from your antenna to your STRs, where you collect the signal ultimately, you have to perform very precise phase matching, because you don't want to introduce an additional unknown instrumental delay, because that influences your fringe pattern. It gets shifted, so you don't want to have this, because that kind of creates different effects in your imaging process later on. So cable length measurements were performed, and then ultimately a phase offset measurement was done, and the correlation vectors that we are measuring are then rotated accordingly to the phase offset. And so lastly, we had a 4-minute time offset to the local noon time, and therefore you can kind of get an idea of your tilting of the east-west alignment of our setup, which in this case is about 1 degree offset from the east-west alignment. So we are pretty much very good in the east-west alignment, and that's also very easy for the imaging process then later on. And another fun part that we could do due to the solar flare observations is that we could check the linearity of our system. So we get an idea if we'll have a different power signal, if our system is still linearly correlated to the data that we receive. And that's the case, as you can see here in this plot. There's no saturation limit in this case. So we are hopefully or observing also very intense solar flares in the future. What I also talked about in one of the SARA meetings is that we wanted to do observations with larger baselines because the 10 meters are not enough to resolve the sun. Therefore, you need 24 meters at least. But doing the measurements with the larger baselines, we use longer cables. And as you can see, normally what you observe is that when the sun enters the field of view, the power increases. But in our case, the power dropped significantly. So there are some temperature effects on our long cables in the summertime when the measurements were performed. So ideally, you would either put the cables underground so they're a little bit cooled or not directly hit by sunlight so they don't heat up during the summer times, or you need to do some kind of other tricks to cool your cabling. So there's no attenuation dependence on temperature. And the last setup was to get an idea of the system temperature of the setup, so to see how sensitive are we. In this case, it's not the system temperature of the whole setup, but only of one of the stovepipe antennas. So therefore, what you classically do is you perform a hot-cold calibration, and then you can compare the hot and the cold calibration with the Y-factor method, and you ultimately get the system temperature of about 122 Kelvin. Although this is very optimistic in this case, because when we performed this measurement, it was at the beginning of January and quite cool here in Germany, so the LNAs were kind of cooled in this case. So in the summertime, the system temperature is obviously much higher than in the winter time. So we talked a little bit about the setup and the setup testing. So now I will go on and talk a little bit about the analysis software, what you can do with the data or how the data looks like that you collect with the interferometer. So in general, you collect the power signals of all the different antennas. The middle antenna is doubled, obviously, since we're putting it onto both SDRs. And what you can see is that I also plotted the times when the sun is above the horizon, which is here in yellow, and the astronomical twilight, which is in green. So basically you can see that we observe the sun almost from sunrise to sunset in the evening, and you'll see kind of a transit curve with a zigzag pattern. What you can then do is that you'll perform a baseline subtraction and also a Gaussian fit to get an idea of the opening angle of your antenna. For this stovepipe, it is about 80 to 90 degrees, and this will be needed later on in the analysis software. So what we'll see for the interferometer setup is that we'll have a correlation, so the real part and the imaginary part. In this case, I only plotted the real part because the imaginary part is essentially the same, but only 90 degrees phase shifted. And since we have a 3-element interferometer, we are observing for 3 different baselines: east-west, east-middle, and middle-west. So we have 3 different fringe patterns here. And in the lower plot, you can see a zoom in of this correlation to the local noon time. And what you can see is in black, which has a very wide fringe pattern, is the smallest baseline. And then in blue and red are the longer baselines, so finer fringes and better resolution in this case. So what is done with the correlation data from the real part and the imaginary part is that you can calculate the visibility amplitude over the time when the sun is above the horizon, and this pretty much matches the transit curve or the power signals of an individual antenna, but with a more pronounced zigzag mark. Yeah. And in the lower plot, you can calculate or achieve the phase from the real part and imaginary part. And so what you'll now have is the visibility amplitude and phase. So basically a complex number. And what you do then is that you combine the visibility amplitude and phase, and together with the UV coverage of the observation, which is plotted on the left side, which is achieved from the hour angle and the declination of the sun. And again, for the different baselines, so the shortest baseline is again in black, so also the smallest UV coverage in this case. And then also blue and red are the longer baselines. And what you can see is the green dot on each of the baselines is the minimum resolution, so the best resolution. And also in the yellow part is the maximum resolution. And how you can imagine that is that over the day in the morning, the baseline on all the three is basically the shortest, the effective baseline, looking towards your astronomical source. And during noontime, when the sun is at Taos, then you'll have the maximum baseline, and therefore also the finest resolution in this case. So the U coordinate is basically the baseline length in east-west direction, and the V coordinate in north-south direction. So what you'll then do is that you grid your visibility data onto this UV coverage, and then you'll create this dirty map by performing a Fourier transform, and then you can go ahead and perform a clean algorithm, because the dirty beam is the convolution of the true sky image with the point spread function. So basically how your system is responding to a point source, which you can see in the right upper plot in this case. So it's kind of comparable to a double slit experiment in physics, but now with 3 slits, because we have 3 elements. So what the clean algorithm does is that it identifies the peak intensity in your dirty map and then subtracts the PSF, and then you'll have a residual image, and then you'll go ahead and perform this identifying peak intensity in the residual image and then subtract the PSF, and you'll do this until a maximum iteration number is reached, or you can set up a noise level that needs to be reached until this iterative procedure stops, basically. And what you can see is that in this case, since the PSF is relatively wide, we do not pick up all the clean components in the dirty map. We only have basically 3 of these, brighter spots. Therefore, in the residual image, you can see this overcompensation basically by the dark blue circle around the still part of the original source, in this case at the center. So the algorithm is not working ideally if you have a very large PSF. And the point spread function depends kind of on your opening angle and your baseline length. So you should or can play around with these parameters to kind of get a better PSF, so your clean algorithm works better and your source is picked up a little bit better than in this case. What you can also do is from the correlation, you identify the maxima, and then you can plot the fringe period, so the difference between the maxima on during one observation day for the 3 different baselines, and you can basically also simulate this when you have the location of your different antennas, and also from the UV coverage basically. And then you can see that the fringe period, as you already saw in the correlation image for the smallest baseline, the fringe pattern was really wide, so the fringe period is quite large. And if you perform a fit, it does not pick up the values very good. So it's a little bit off in this case. And for the longer baselines, we have more data points, therefore the fit is better. And also it's the fringe period is shorter, which is expected. So basically, this is the algorithm or analysis software that you can work with. And what we did later on, due to the solar maximum currently, we also observed solar flares. And we can correlate this data that we had with other radio data and also to X-ray data. So since we're in Germany, I also used another instrument which is located in Germany to have the same time frame available. So the same time is covered for sun observations. And in this case, the black curve is the power signal from the stovepipe, and the other curves are for different frequencies at this other German observatory. And what you can see in this case, the yellow curve or brown curve, these are the higher frequencies. So what you'll see is that the onset of the flare, in this case on October 3rd, is earlier for the higher frequencies, which tells us that the higher frequencies are from a different wavelength regime. So as I already said in the beginning, depending on the wavelength we are observing, then also we are observing obviously with different frequencies, and then we are observing different layers. And the higher the frequency, the lower the layer of the sun we are observing. So we can basically say that at the higher frequency, the flare onset is at the lower layer, and then the flare travels outwards through the other layers. And what was also interesting to see on May 8th, when we also saw flares, is that if you have a look at the different frequency ranges, then the one that is close to our stovepipe frequency basically shows the same pattern as the stovepipe, but when we go to higher frequencies, then the flare in the morning between roughly 8 and 11 o'clock in UTC time frame is not visible in the other frequency ranges. So again, this tells us that either the emission process is different at the higher frequencies, or that the layer where the flare originates from is at a higher level than the higher frequencies. So you can learn a little bit about the place where the flare originates from by comparing or observing at different radio wavelengths. And what you can also then do is compare your radio data to X-ray data. And what you'll see in this plot, in this case, in the black curve again, is the stovepipe antenna, the power signal for May 8th. And then the colored vertical lines are flares observed in the X-ray regime. And what you can see is that it does not match very good with the radio data. When you have a peak in radio data, that does not automatically mean that there is a flare in the X-ray regime. And what is also quite interesting to notice is that we have a longer flaring time during the morning, and then a very intense flare at 12 o'clock. And afterwards in the radio regime, there is no flaring anymore. But in the X-ray regime, there is still a lot of flaring going on. So what you will need to know in this case is that for the intense flare at 12 o'clock, there's also a coronal mass ejection happening. So what you can basically learn from this is that in the radio regime, there's a little bit of pre-flaring, and then there's an intense flare with this coronal mass ejection, and afterwards there's nothing. But in the X-ray regime, there's constantly flaring going on. So this tells us also that the emission mechanisms in X-ray and radio are different. They're not the same. And also that the radio flares, the intense ones, are mostly connected to these coronal mass ejections. And as a last step, what you can also do with the interferometer data is that, again, you can have a look at the fringe period. And in this case, it's the same observation day, May 8th, as presented before with the power data. And what you can see is where the intense flare at 12 o'clock happens, there's a strong variation in the fringe period. So when you have a look at the correlation data and also in the interferometer data, then the flare is also clearly visible here. And this fringe period variation, normally the fringe period tells you about the resolution. So the lower the fringe period, the finer the resolution you're looking with your interferometer. But since there is no clear tendency whether your fringe period drops during the occurrence of flares or is higher, you cannot deduce whether your resolution in this case changes. But you can get an idea that there is something happening with the resolution or with your fringe period. So you get the idea that you're observing not the sun right now, but more the sunspot and the solar flare occurring in this case. So what we'll do next is that we'll go on to smaller dishes. So at Astropilot, we also have a 1 meter and 2 meter dish, which we can connect for observations, and we have a maximum baseline length about 53 meters then. So enough to resolve the sun. And also we have dishes now, so we are a little bit more sensitive. So there are advantages and disadvantages to this setup. We're a little bit more flexible because we can now not only do transit observations, but also tracking observations. Of course, we are having a smaller field of view, so we are not overpowered by the sun. But at the same time, since we have the smaller field of view, we need to be precise in location and with our pointing. And still, sun is still a problem. It may enter through side lobes. And of course, now the problem with this new setup is that we are not exactly in east-west alignment. So when you want to do the imaging process, it's a little bit more complicated whether you can actually apply the Fourier transform. And another issue is phase matching in this case, because we could not specifically measure it with the instruments we had available. So there might be a little, instrumental delay, which we are not, certain of. So what we did is, again, transit observations, in this case, first with the sun. And here you can already see the correlation again, the real and imaginary part. And what you also see, since we only have one baseline, we only have one real and one imaginary part. And what you can also see in this plot is a flare occurring, where we have these higher intensity values. And then, of course, since we are now observing with dishes, we are a little bit more sensitive, and we can go ahead and also measure other bright radio sources. So, for example, Cassiopeia R is visible in the correlation of the interferometer, and also Cygnus. We also tried it lower intensity sources like Taurus, but what you'll see here is different fringe patterns appearing also with different intensities. And what happened in this case is that we did not observe Taurus here, but we observed solar flares on this day entering through the side lobes. So if you want to observe lower intensity sources, then ideally you would perform the measurements during nighttime where you don't have any influence of the sun through side lobes or main lobe. So what you, as I already told you, is that we can also perform tracking observations. So in this case, this is a tracking observation from morning to evening. So again, sunrise to sunset almost. And what you'll see in this case is you don't clearly see the fringe pattern only in the morning and in the evening when the baseline is very short, so therefore the fringe pattern is very wide. And in the other case, you see again the correlation amplitude, and you have certain points where there is a maximum, and then there are these node minimum points appearing, and also again a flare on this observation day happening, and we have 3 different nodes on this day. So basically what happens is that you will observe again from morning to afternoon and then evening. So the effective baseline over the day changes. So in the morning you are very short, and then the baseline increases until noontime, where you have your maximum baseline length, and then it decreases again for the evening session. So when you will then go on and plot the visibility amplitude against the baseline coordinate in the east-west direction, which is the U coordinate, as I already told you earlier, then you'll see this kind of behavior. So again, the visibility amplitude rises and then it decreases until you reach this minimum point or 0 point in this case, and then you'll get basically a side lobe effect, and then at noontime you reach the maximum baseline length, which is about the 53 meters, where in this case the flare occurred. And what you can learn from these kinds of observations or plots is about the shape and size of the object. So what you do is you identify the 0 point in your plot, which is at 27 meters roughly, and then the size estimation can be calculated with the angular resolution formula by inserting your observation wavelength and then your baseline length where the 0 point is occurring, and then you see that you have for the sun a size of about 0.45 degrees, which is pretty good because in L-band we expect something about a half degree. And what we also can learn from this is that not only the size, but the shape. And since we have a 0 point and then again a maximum, we can deduce that it is a uniform disk, because if we observe a Gaussian source, for example, then you don't have these 0 points, and then again the maximum, you only have a maximum which kind of decreases. So you can use these kind of observations for different sources to get an idea of the shape and size without actually performing any Fourier transforms to create an image of the source. So a little bit about summary and what you can do in the future. So we talked about the fundamentals of radio interferometry, then the setup design and testing, essentially linearity, phase matching, and then tilting of the east-west alignment, and the issue of long cables. And then I showed you a little bit about the analysis pipeline, how the imaging process is working, And then we had a look at the fringes of the sun and also solar flares and their connection to the radio and X-ray observations, and also the fringe period variations during flares. And what you could do in the future is you can extend the setup, basically using more than 3 antennas, maybe also try larger baselines, and maybe also incorporate dishes. So you're a little bit more sensitive, but of course you're limiting your field of view then. You can do solar observations. So in general, you could monitor the sun for a large period of time. So again, since we're in the maximum of the solar cycle currently, you could go on and measure or observe new flares. And also, maybe if you do very long observations, about 11 years or so, or 22 years, then maybe you can also see solar cycles. So basically power variations in your antennas. And you can also check for the longer baselines how your interferometer is responding, and maybe if there are any effects of the flares in the imaging process. Since we observed flares with this setup, you can also try to kind of create a polarimeter and check if the flares are linear or circular polarized. And in our case, since we're at the Stockholm Observatory, we also have different other instruments, and then we can kind of transfer the analysis pipeline and the observations performed with the stovepipes to other setups, for example, the 1 and the 2 meter interferometer, and we also have a KU band setup, but this needs a little bit more of mechanical improvements. So we are working on this, and maybe in the future we'll, when we are ready, we'll do observations in this frequency range as interferometer setup, and yeah, tell you about our progress that we do there in the future. Well, that's all that I have for today. Thank you very much. Do you have any questions?
I have a simple one on construction. You have these 3 antennas. What keeps insects from living inside the antennas? What did you put on this edge?
So in general, they have a reflecting end cap, and yeah, I forgot to mention it. They also have a white lid, so there's no water entering. Ideally, there should be no insects living in there, but you never know, through some sites they may enter. But in general, they're clean of insects, I would say.
How did you find a cap that would fit?
We 3D printed one specific for the setup.
Perfect. Okay.